Alright, let's get into Chapter 18, Thermodynamics, Entropy, Free Energy, and Spontaneity. I want to start by talking a little bit about the last term, spontaneity. In chemistry and physics, the term spontaneous refers to a physical or chemical process that, once it begins, proceeds on its own without external influence. A good example of a spontaneous process is shown here. If we have two containers separated by a valve, where container A contains a gas while container B is essentially an empty vacuum, and we then open the valve, the gas will expand until it fills both containers equally. Once the valve is opened, this expansion happens on its own, so it's a spontaneous process. An important idea that we'll come back to several times is that any process that is spontaneous will not be spontaneous in reverse. In this context, if we leave containers A and B filled with a gas, and leave the valve between them open, the gas will never spontaneously move out of the container B and only stay inside container A. It's important to note that the fact that a process is spontaneous does not say anything about how quickly it will occur. For instance, the rusting of iron in air is a spontaneous process because it occurs naturally, without outside input, but it still happens quite slowly. The speed at which a process occurs doesn't tell us, then, about the spontaneity of that process. If you think back to Chapter 14, on kinetics, a slow process is just one with a high activation energy barrier. How can we predict if a process, or really in the context of chemistry, a chemical reaction, will be spontaneous or not? To get into this discussion, let's recap a few things that are going to come up a lot in this chapter. First of all, one of the main thermodynamic properties of a chemical reaction that you've seen before is its enthalpy change, or essentially the heat change in a reaction. Something we've discussed before, but we'll get into more detail on in this chapter, is entropy, which is abbreviated S for reasons that I'm still not quite sure about. There's a few related ways of thinking about entropy, and it can get complicated pretty quickly, but suffice it to say for our purposes that entropy is a measure of the amount of molecular randomness in a system. Since physical systems tend to minimize their potential energy, you might be tempted to think that a reaction will be spontaneous based on whether it's exothermic, since a lot of common chemical reactions are, in fact, exothermic, and exothermic reactions result when the transition from reactants to products results in a decrease in potential energy. So for instance, is the combustion of methane, the main component of natural gas, spontaneous because it ends up releasing a bunch of heat, like it does when used to power a gas stove? Unfortunately, it isn't that simple. While lots of reactions, especially ones that occur quickly, are exothermic, there are plenty of reactions that, at least under certain circumstances, are spontaneous without being exothermic. For instance, the melting of ice at temperatures above 0 degrees Celsius, the boiling of liquid water above 100 degrees Celsius, the decomposition of N2O4 into NO2, or the dissolution of sodium chloride in water are all spontaneous processes, but you can see here that they are all endothermic to varying degrees. To explain why some reactions are endothermic and still spontaneous, we need to incorporate entropy. For any given substance, including but not limited to water, the solid phase is going to have the least randomness or disorder compared to the liquid or gas phases, and the gas phase will have the highest disorder compared to the other phases, with a liquid being intermediate between gas and solid. Like enthalpy, entropy is a state function, meaning that the change in entropy for a process or reaction only depends on the entropy of the final and initial states, and not on the path taken to get from the initial to the final state. As a result, whenever a substance transitions from a lower entropy state to a higher entropy state of matter, the entropy change of the system, delta S, will be positive and vice versa. So endothermic processes like melting ice or boiling liquid water result in an increase in the entropy of the system. There are other situations where we can predict that a reaction should result in either an increase or decrease in entropy. Let's consider the decomposition reaction of N2O4 into NO2, which we saw as an example of an endothermic reaction a few slides back. The balanced reaction shows us that for every mole of N2O4 that decomposes, 2 moles of NO2 are generated. Because both of these substances are gases at room temperature, this means that the forward reaction results in an increase in the number of gas molecules. Because gases are highly disordered, it makes sense that this would result in an increase in the entropy of the system. And of course, this also means that the reverse reaction results in a decrease in the number of moles of gas particles, and hence a decrease in entropy. Finally, that last example of a spontaneous endothermic reaction we saw, the dissolution of sodium chloride in water. There's two things going on here, the dissolution of the crystalline solid and the hydration of the ions by the water molecules. The dissolution process breaks apart the highly ordered crystalline lattice of ions, so it increases the disorder and entropy of the system. However, the hydration of the ions, where the polar H2O molecules line up with the partially positive hydrogens near the anions and the partially negative oxygen atoms near the cations, increases the ordering in the system and hence lowers the entropy. The overall entropy change, therefore, will be the net combination of these two effects. In the particular case of sodium chloride, and for most solutions formed by dissolving solids in liquids, the net effect is that the entropy increases as a result of the dissolution, although sometimes the effects are weighted differently and there can be a decrease in entropy in forming a solution this way for other compounds. To quantify the entropy change of a chemical reaction, we have to define the entropy of any given substance in any state. The baseline assumption, encompassed in the third law of thermodynamics, is that the entropy of a perfectly ordered crystalline solid substance is equal to 0 at a temperature of absolute 0, or 0 Kelvin. As the temperature of a substance increases, so does the kinetic energy of its particles and hence its randomness. So entropy increases with temperature, hence defining a crystalline solid to have 0 entropy only at absolute 0, or again 0 Kelvin. If we incorporate this notion and look at a plot of a substance's entropy versus its temperature, we see the relationship shown here. Entropy increases as temperature goes up, but in particular, there are discontinuous jumps in entropy at the melting and boiling points due to the jump in entropy associated with the phase change from a lower entropy state of matter to a higher entropy state of matter. For 1 mole of a given substance in a particular phase of matter at a specific temperature and 1 atmosphere of pressure, we can define what's known as the standard molar entropy. These values are known for many common substances, and are listed in an appendix in your textbook alongside other thermodynamic properties, like enthalpies of formation. Some representative examples are on these slides, showing that, as we would generally predict, the standard molar entropies of gases are higher than those of liquids, which are higher still than those of solids, particularly crystalline solids. Of course, you don't want to memorize any values here, that's what the appendix in your textbook is for, but we can use provided values like these to, for instance, calculate the entropy change for a chemical reaction much in the same way that we can use enthalpies of formation to calculate the enthalpy change for a reaction given its reactants and products. If we add the standard molar entropies of the products together, and do the same for the reactants, and then subtract the sum of the reactants from the sum of the products, we can get delta S, our entropy change for the reaction. For instance, let's go back to that N2O4 decomposition into NO2 example. The standard molar entropy for nitrogen dioxide is 240.0 joules per mole Kelvin, and the standard molar entropy for dinitrogen tetroxide is 304.3 joules per mole Kelvin. Accounting for the 2 in front of NO2 in the balanced equation, subtracting products minus reactants gives us positive 175.7 joules per mole Kelvin, confirming our intuition from earlier that increasing the number of gas molecules as we proceed in the forward direction also results in an increase in entropy overall. The importance of entropy with regards to spontaneity is this, stated in the second law of thermodynamics. For any spontaneous process, the total entropy of the system and its surroundings must increase overall. Notably, the entropy of either the system or the surroundings can decrease as long as the entropy of the other increases enough to result in an overall increase between the two of them. And going forward with this, we need to remember that the first law of thermodynamics, one that was introduced in Chem 1211, that any process, whether it's spontaneous or not, the total kinetic energy of the system and its surroundings will be constant. We can convert between potential and kinetic energy, but not create or destroy energy overall. We can express the principles of the second law of thermodynamics in the equation shown here. For some process, like a chemical reaction, the sum of the entropy change of the system and the entropy change of the surroundings is the total entropy change of the universe resulting from the process or reaction, which we call delta S total. If this delta S total is positive, the reaction or process is spontaneous. If it's negative, the reaction or process is going to be non-spontaneous. If it's exactly equal to 0, the process or reaction mixture is already at equilibrium. What do we mean by the change in entropy of the surroundings, though? It comes down to the fact that the entropy of the surroundings is affected by whether the system, or reaction, is endothermic or exothermic. With an exothermic reaction, heat is released, and hence the temperature and the entropy of the surroundings goes up. In the reverse case, where the system is endothermic, heat is absorbed from the surroundings and the temperature and entropy of the surroundings goes down. Because the sign of delta H and the temperature change are opposite, the change in entropy of the surroundings is proportional to delta H, but specifically negative delta H. Taking into account that the change in entropy of the surroundings is also proportional to 1 over the Kelvin temperature, the overall result is that the equation highlighted here, the change in entropy of the surroundings is equal to the negative enthalpy change for the reaction divided by the Kelvin temperature.